record on this computer. Okay, so I'll get started in a bit, but today is going to be definitely more of a day where I'm lecturing because for loops are one of those things that students have issues with. And so I'm going to go over these in more detail today about how they work. Desktop, I'm going to call this use the force. There we go, because I got to get in my data jokes where I can. Does anybody know what the difference between a bad joke and a dad joke is?
The first letter?
Yes, the first letter. Yeah, I can take demos after class. Generally speaking, my schedule is thus. I start heading in around I start commuting around 7:30. I get in around 8:30 for my class at 9:30. And then I have a 3-hour break between classes, 1 hour of which I dedicate to office hours. It's not too bad because I'm going via bus to train. And while I do have to wait a bit on for the train to start, you know, my train is the last stop. So that makes it, you know, I'm able to get a good seat. And then anyway, my train back doesn't leave until 4 o'clock. So I've got that amount of time. You know, I've got at least a half an hour to take demos basically and answer questions. So don't feel like you're imposing on me. Yeah, I feel your pain. My favorite place for living the train commuting life was Japan. When I was there in at Temple, Japan for a summer. By the way, I should talk about that because for those of you who don't know, which is pretty much everybody, I am kind of one of the unofficial coordinators for making sure the curriculum at Temple, Japan is the same as I will explain that later, but basically that's just, if you have more questions, but basically that's completing the problem and then showing it to me. So Temple, Japan. Temple has 2 satellite campuses, Rome and Tokyo. I've been working with the Tokyo campus on a unofficial basis, which is basically that they ask me, but I don't really have an official title or role or anything, about coordinating. And I've been working with them to coordinate because I like the campus a lot, but making sure that our curriculum there is up to snuff, and that we've got similar stuff going on there. I taught there for over the summer in 2018, and I've taught remotely this previous year because I couldn't travel there during the pandemic due to the pandemic. But we have a campus on Tokyo, and you could stay there and you can take all the courses you need to get a computer science minor at TUJ. So at Temple, Japan. So if you're interested in that, just keep that in mind, because maybe things will get better by summer 2022. So just worth thinking that. I don't know how tuition rates work for out-of-state students with regards to that. I don't know what the difference between in-state versus out-of-state tuition is for Temple. I know that it's higher. I just don't know to what degree. But when I was at Georgia Tech, I do remember being one of the key points for studying abroad, if you were an out-of-state student, was that you were paying in-state tuition while you were studying abroad, thereby making studying abroad cheaper than studying on the actual campus. So just there might be financial benefit to doing that as well. I don't know. It's just worth keeping in mind. But regardless, if that's something you're interested in, keep it in mind, because and I can, I could direct you to talk to the appropriate people about what courses are going to be offered there. So I have no idea because I don't know what the Japanese government is going to do. The Japanese government right now, the Japanese populace isn't. Polling shows that basically that the current prime minister who's taken over Abe, Prime Minister Suga, is very unpopular due to his handling of the coronavirus. It doesn't help that he basically took over after the retirement of a very popular prime minister. And the vaccination efforts for some reason have been really slow. So I don't know. I don't really know what's happening in Japan. I know that I think there are some in-person classes in Japan. That's more to the case of the Olympics, because there was a lot of pressure to do the Olympics and not delay it a year. Although personally, I feel like there's no reason not to delay it a year and just done it during run the Winter Olympics and the Summer Olympics in the same year. But that's a whole nother story. What's important, I mean, it does help that basically that wearing masks was something I can personally test to being a widespread practice there beforehand. You'd see because of allergies due to replanting efforts. But that's another story for another time. So for loops, that is what we're going to go over today. So today we are not doing an in-class exercise. Today I'm going to be lecturing because I want to make sure that this is covered appropriately. Now there's going to be some annoying math that I'm going to do, and I'm going to try to make it as painless as possible and as accessible as possible, because I know a lot of you want to avoid math as much as possible. That's not me. I love my math. And I feel like the more math the better a programmer that makes you. But that doesn't mean that you need math to succeed at programming. It's just like another tool. And it's another way of building those mental muscles. But, that's just because my mind is weird and that's the way it works. So we learned about the for loop. And we have this, which is this magical statement right now, which was, and I'll write it like this, for blank, and I'm going to be constantly writing and rewriting this, by the way. So hold on, let me share my screen. Yep. I realized that I was typing. There we go. And now everybody's on the bottom. So the magical statement for the for loop, for blank in range, and then we put any number we want, which is the number of times we want this for loop to run, which is range. Let's see, print. Everybody can see the screen now though, right? Okay.
Yeah.
Okay, print. Hello. So this will print out the string hello 5 times. Oops, there. And okay, what's going on here? Save. There we go. And run it. So this for loop prints out hello 5 times because I told it to do 5 times. This is kind of the most common structure we'll use, which is we tell this algorithm to run a certain number of times, or this statement to run a certain number of times. But what's actually going on here? What is a range? So interesting thing you can do in Python is that you can print out stuff. It doesn't really have an effort. If I print out range, notice the lack of parentheses. Notice that it comes up purple as well. That indicates that it's kind of a built-in function. It says class range. Okay, that doesn't really give me much. Okay, what about if I print out range 10? It's going to tell me range 0 to 10. What? Doesn't really tell me much there. Okay, wait, does that mean that I can do this as well? So I'm just going to jump ahead to kind of show you what's going on here, which is that a list is that this is generate that in older versions of Python, this would generate an actual list of numbers. Here it is actually, sorry, it would create an actual list of numbers. Here it's generating that. What does it mean? It's doing a memory efficient thing where it's just creating these numbers one at a time. I can force it to create, and you don't need to know this at this point. I can force, this is for demonstration purposes only. I can force the list, this range statement to tell me all the values it's going to have. And now that I printed out, so here what I did is I said range 10, and because that was giving me this over here, and I threw it into this magical thing called list, which no idea what that is. But if you guess it's like int and like float and like string, it turns whatever you throw into it into a list. What's a list? Exactly what it says on the tin, but we'll go into more detail about it when we cover lists in properly. But the point being is that we've got all these numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10, interestingly enough. What a range is that it actually gives me this mathematical range. What range is it's a range of numbers. And to use mathematical notation, when I write range 10, I'm generating this mathematical range, which is 0 up to, but not including 10, which is a weird notation. It seems like weird to arbitrarily do it 0 to 10, but the reason is because, as we'll see later, this makes subtraction really easy. And to figure out how big the range is. But that's what's going on under the hood. So as a result, I can do something interesting. Yep, the numbers in the range are automatically integers. So if I say 10, watch what I do over here. For blank in range 10, if I change this to value, and I print out value. So here, right, I was just having whatever here. Now I'm going to print out, I'm going to say for this. Now, this is why we call this a for each loop, because we can read this now as the following. For each value in range 10, print out that value. So for each value in the range of 10, specifically what range 10 is a shortcut for 0 to 10. For each value in the range 0 to 10, print out that value. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I say this range, I'm talking 0 up to, but not including 10. Have I lost people so far? Okay.
What is the use of doing that instead of just doing list?
Memory efficiency.
Okay.
Each of these values is only existing for the duration of the for loop. A range is what we call a generator. And that means that I'm going to give it a value. It's going to provide me with a value each time I call it. It's a pretty cool thing. And Gilan, I see your question, which was what the blank before. And Jacob, that's correct. It is just a placeholder. Do you have to put a starting and stopping point in the range? The answer is you have to put a stopping point in the range. You do not have to put a starting point in the range. And that brings us to our next point, right? So here, range, if we actually type it out here, watch this. It says range start. You have you can do it a couple ways. Range stopping point and range start, stop, and step. So what's cool here is that I can do range 0. So first off, range 10 just means range from 0 to 10. So how does the for loop know that we need to move on? Because you get to the end of the indented block. That's how it knows. it knows it needs to move on by getting to the indent. Run. Okay. So the for loop know to move on to the next value. I mean, it just goes on to the next value, but once you're done with all the indented statements. Like so. Right? So here and here, I'm going to actually put in a new line to help spread it out. So printing 0, done with this value. Printing 1, done with this value. Printing 2, done with this value. So here I've indented this these 3 lines. So those 3 lines will be part of it. Anything outside of it will only, once we are done with the for loop, we'll go back to the unindented stuff. So here we go through, done with the value, and then just plain old done at the end. The /n over here, great question. It's what generates this new line. /n creates a new line. It's easier than just typing it's what I'm doing there is the equivalent of me doing this, which is so it was just a quicker way of doing that, so of creating a blank line. Okay, so now going back to the question of range, we can mess about with range quite a bit. We could do 5 to 10. And let's go ahead and comment out these things so that it's just easier to read. So we're only going to print out the numbers that we need. Five, 6, 7, 8, 9. So here we're saying start at 5, go up to, but not including 10, right? Annotation again. Draw 5. I said draw 5. So start at 5, go up to, but not including 10. Now, like I said, the math makes this a bit, the reason this kind of works for us is that the math is easy. How many numbers are in this range? How many times will this loop run? Right? With range 10, it was easy because I just simply said, if you saw the number 10 in there, it was great. Here, though, I can tell you that it's going to print out 5 numbers. Why? Because the stopping point minus the starting point is always equal to the number of numbers. So 10 minus 5 means that I've got 5 numbers I'm going to print out. So doing it with this range of not including the first, but not the second, really makes sure it ensures that that the math is nice and easy, which is always nice. And I can make this pretty arbitrarily large, 5 to up to, but not including 100, right? And that's going to have 95 values printed out. Not going to go and individually count them here, but you could work out the math on that. Now, yes, printing out stuff is very manipulatable. We'll get into that in a bit more detail, but I want to focus on the for loop here. So the last thing we can do with a range is I can add an optional third step, which is the step point. And if I run this over here, we notice we printed out a lot less numbers. We did 5, 10, 15, 20, 25, 30, 35, 40, so on and so forth. So by default, you're just increasing up by 1, right? Here with this range, we are saying start at 5, go up to, but do not include 100, and go up by 5s, which is what we did. Make sense? So it's very powerful. We're going to use that. We're going to use that not so much here, but we will use that occasionally. Most of the time, you'll just be dictating your range, and the vast majority, it's going to be like this, where you're just going to run something a couple of times. But the important thing here is that we read this as for value in the range 5 up to, but not including 100 for each value. Similarly, and I'm just going to comment this out so that it's going to remain there. Similarly, we can do things with other values. So for instance, for letter in, say, word is equal to hello. For letter in hello, for letter in word. Now, for those of you coming from, now I'm going to just, for those of you who are coming from a different programming language, I'm just going to interject for a second. You may be wondering, wait, you're doing for loops. Where's my indices? Where's my indices? The answer is that actually we don't care too much about the index unless we want to change something, in which case we'll use something called enumerate to do that. But for right now, just know that this is kind of a different type of for loop than you've been working. This for loop is similar yet different to what you're working with, okay? It's a different tool. So for letter in word, print, for each letter in the word, print out the letter. Yeah, it is the enhanced for loop from Java. That's exactly what it is. I like to call it the for each loop because that's what it is, as opposed to the for I loop, which is useful for indices. But the point being is that they're both different types of what we call definite loops, meaning that we can tell how long it's going to run. Well, excellent question. So one of the students direct messaged me and asked, in lab 4, you have a 99 bottles of beer on the wall song that we've got to do. How do you do that? Which is what I had been thinking. Okay, make sure you don't forget this. I almost did. So there is one more thing we can do with our range. So we can go backwards in our range. Nothing's stopping you from going backwards in your range. From 100 to 50 minus 1, right? But here's the kicker. Let's go down to up to, let's go to down to, but not including 90, right? It's still not going to include that endpoint. Right? So be careful with that. Another way I could do that, by the way, is that I could do some interesting things with subtraction, but it's just useful to know that you can go reverse in the range. There's nothing stopping you. Just requires you to like kind of just realize you can manipulate things however you want. You had to use the third number to dictate the fact. So you need to use 3 numbers, one for the start, one for the end point, and one to say how you want to go there. If you didn't use this one, it would assume you wanted to go up, and the range from 100 to 90 does not exist. Ishan, if it works and it's built into, if that's built into Python, sure. There's nothing, I am okay with you doing research to figure out easier ways to do things. Okay. So now that we've kind of got an understanding of the way the for loop works, let's talk about our object lesson for today, which is pi. Okay. So for pi, for those of you who need a refresher, right? We write that out as like 3.1415, etc. Right? And we see it used in the formula that we used on Tuesday for circles, right? Which is that the circumference of is equal to 2 pi r, or actually more accurately, our circumference is equal to pi times the diameter, which is twice the radius, right? Right? So that means that that really pi is the ratio between the circumference and the diameter, which is 2 times the radius. Okay, so and I know that seems a bit weird that it's just this ratio and we're just trying to figure out this value of a ratio. Again, I'm a big lover of Wikipedia. There are issues with Wikipedia. But I do love it for a lot of their information over here. So let's go to Wikipedia for pi. And there's, yep, see the circumference of a circle is slightly 3 times longer than the diameter. The exact ratio is pi. There's used to be this wonderful GIF or GIF, I don't really care how you pronounce it, about how you could, of it unfolding. And just seeing that basically a graphical proof, oh, there. Right, so there's pi. There's a circle that is of 1 diameter. And if you roll it out, you see it comes out a bit longer. Everybody see that? Yeah, so now the question is, how do we calculate that value though? Right, so first off, pi is an irrational number. That means that you cannot, just use a fraction to give me an answer. But there have been approximations of pi like throughout history. So here we go, and approximations of pi. One of the earliest approximations is kind of like what we were doing, is something we were doing on Tuesday. See, I like draw everything together, where what you could do is that you could estimate pi by creating a polygon of a high enough degree. Okay. And the perimeter of that polygon would eventually be equal to would be close enough to the diameter of the circle that it is being overlapped with. And that's kind of the technique that Archimedes used, but I don't like it because it involves trigonometry, and I hate trigonometry. I don't actually hate it. I just hate having to do it when I've got a computer that can do everything for me. But now, on the other hand, one of my favorite approximations of pi. So, so point of just a bit of history, Babylonian mathematics usually approximated pi to 3, sufficient for architectural projects of the time. Notably, this was reflected in the Hebrew Bible, the description of the Solomon Temple. I mean, they knew that pi wasn't, wasn't equal to 3, but like, check out the Hebrew alphabet and how they did new numbers. Wasn't exactly the Hebrew, alphabet wasn't exactly designed for high level decimal system stuff. Anyway, you've got the but now I think it's le hue. If there's a Mandarin speaker, please correct my pronunciation. Very famous Chinese mathematician. He created this wonderful approximation of pi. And then Zhu Chongxi, he computed he gave approximation of pi of 355 divided by 115. Now we can actually go to our terminal right here, which is pretty cool, and do 355 divided by 113 and see that that is 3.14159. And the next value I think should be a 6, right? So that's actually very close. Like, that's close enough that for pretty much everything you need. So once we got to the Middle Ages and beyond that, we started getting different approximations and formulas for pi, for computing pi. Now, one of these, what we call is going to use a let's see, chronology of the computation of pi. Last 100 decimal points of the 2020 world record computation are. So we can see that the number of decimal digits of pi that have been computed has been basically skyrocketed as computers got more and more powerful. Let's see. So I believe it's the Leibniz Formula. Yep, it's the Leibniz Formula that I would like. So in the year 1400, Madhava of Sangamagrama, he discovered what's currently called the Leibniz Formula for pi, but because, because of the way history works, Leibniz got credit for it. Although, as we can see here, that there have been, changes in proposals as to different naming things, But anyway, let's go and look at this formula. So this formula states that 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. If we, as this approaches infinity, if we were to take this all the way to infinity, which is impossible, right? You can't take this all the way to infinity because then it would never end. But as it approaches infinity, this, if we could, it would hit pi over 4. Okay, so this is what we call a converging series in mathematics. It's an alternating series here, and you can see that, and the alternating refers to the fact that we've got a minus, a plus, a minus, a plus, a minus, a plus, a minus, plus, right? It's swapping values each time. Okay, but the idea here is that the more numbers you add, the more accurate this is going to get to being pi over 4. Does that make sense? So series like this are covered in calculus 2, and proving that they converge is for calculus 2, but we don't need to prove it. I mean, these mathematicians, they did it all. Oh, they did all the hard work for us, so let's take it and run with it. 1 minus 1/3 plus 1/5 minus 1/7, all the way up to, if we do that enough times, we'll be getting pi over 4. Okay. So first off, you don't really need to calculate or remember pi. So let's go ahead and make a new file. I'm going to call this one easy as pi, because of course I am. So first off, if I want pi, I'll import math. Yes, I know that seems. So what does importing math do? Well, it gives me access to a bunch of, that lets me use the math package, which has a bunch of things like math.py in it, which just has a value. Let's see, no attribute pi. Is it lowercase? I always forget because I'm dealing with multiple languages here. There you go, it was lowercase. And in Java, it's uppercase. Okay, math.py, it has a math. So the math function has, the math package has stuff like that. The math .e, right? It's got other constants in there like that. So if I want to know what pi over 4 is, I can just simply do math.py divide by 4. Now, note that even though now we all know, as I pointed out, that since pi is an irrational number, this should technically be a lot longer, right? But your computer uses floating point numbers, the IEEE double precision standard for floating point numbers, which means that these are 64-bit numbers. That means there's a limit on how many digits it can store. So simply put, this is as close as your computer can get, and that's enough digits. Trust me, that is enough digits to use. So as we do an approximation, it should get closer and closer to this. Okay, so I'm going to swap back to the other file for a second to talk about another kind of thing we can do with the for loop, which is one of the most common things we can do, which is called the practice of accumulation. The accumulator pattern, we sometimes call it. What does that, and what do I mean by that? That means that I am going to use addition to do some kind of summation. Okay, so here, what I'm going to do is I'm going to do for I in range. Let's go. I'll go with 5. Print I. So I'm going to start this off and write, what will this print? Right? This will print out 0, 1, 2, 3, 4. Right? 5 different values. Just to refresh your memory on that. Okay. Now, why did I put I here? Because I is the most common thing we use. I for integer, I for index a lot of the time. So I is very commonly used as a variable. It is not, in this case, the square root of -1. Okay, you can be more specific and say value and stuff. Just make sure that what you have, Matt, you know, that this value and this guy are going to match.
Professor?
My screen's frozen.
My screen is frozen.
Your share screen is.
Yeah, we can't see what you're typing.
Oh, okay. Yeah, Zoom's been crashing even though I updated it. It's weird. So let me go ahead and I'm going to kill Zoom and I should rejoin very quickly. Okay, yeah, this is an issue. It is not, but okay, weird. Okay, didn't need to kill it. Let's see what happens now. Weird. Task manager. Yeah, this is a Zoom issue. This happened on Tuesday, if you remember, but that was a different computer. So I assume that the latest update broke something. Yeah. Yeah, I'm just going to blame the latest update. So, okay, and I'll drop you down to the second screen. Open up the chat window. Okay. Sorry about that. I don't know why I wasn't seeing the chat either. I can see all those chat messages, all those frantic chat messages now. Okay. So, right, we've got this for loop, I in range 5, right? And that, it doesn't matter what I call it. I use I a lot of the time for integer or index. So what I'm going to do here now is I'm going to create an accumulator pattern. I'm going to call it total is equal to 0. And now watch this. Total is equal to total plus I. Now be equal to 10. Now, if you notice, adding 0 plus 1 plus 2 plus 3 plus 4, if you add that together, that's going to be equal to 10, right? 1 plus 2 plus 3 is 6. 6 plus 4 is 10. Okay. So how in the world did that work? Well, let me go ahead and print out, let me add some print statements. Print I is oh, now I know what I want to do. Sorry. I is, and now let's say comma I and then /t. /t puts in a tab, by the way. This is used for separation. Total is I know. Okay, yeah. Definitely yeah, it's going to be reversed otherwise. Total is, comma, total P, I is I. So if we run this, we'll see that total is 0, I is 0. Okay, in our first stage of the loop, right? So I, right, will be the values 0, 1, 2, 3, 4. Everybody get that? It's going to be those 5 values over here. Okay, so total starts out at 0. So what we do is, yep, the /t created a tab. And the reason I put that /t in is that it makes this look it makes this spread out much nicer than if I didn't have it. Let's see what happens if I don't have that tab. Right, it just looks like a giant run-on sentence, whereas if I put in a tab, it makes it look tabled, which is really cool, right? And very useful. It looks a bit weird with the like /t, you know, looks like I'm writing something there, but anything that you've got a slash, that's warning that it's a special command. So total is total. So we start out, total is 0, I is 0. We're going to add them together. 0 plus 0, store that in total, that becomes 0. Let's go on. So that's our first way through. Now we go, what would happen if we put the number first and then the sentence? It would change. It would change the what total is. It would show what total is after we add something rather than before. Okay. Anyway, let's go on to this. So now we are at I is equal to 1. Total is currently 0 and I is 1. We'll add 1 to 0. Total is 0, I is 1. We'll add 1 in and we'll store that in total, which makes it 1. So now I becomes 2. If we check in and see what total is 1, I is 2. So now what we're going to do is we're going to take total, which is 1, add 2 to it, right? Because we're at this point, add 2 to it. That becomes 3. So we're going to store it in total. So total becomes 3. Then now it's I is incremented to 3. So we add 3 and 3, we get 6. Now we go into the last step of our loop. Total is 6, I is 4. Right? And then what we're going to do is we get total is equal to total plus I, which would be 10. I'm going to do something a bit tricky here, just simply that we can see it all in one line. So this is going to look a bit weird, but it's a really useful thing. And it's better to see what's going on when I do this. So you might not have seen this yet, but watch this. So after adding, total is and I forgot to add this. So now I've got to make this a bit bigger. So what did I so now our output is total is this, I is this. After adding, total is this. So what in the world did I just do? I have 2 print statements executing 5 times, but I have only 5 lines. So what did I do with this special end is equal to blank? So print in Python is actually extremely powerful, which has a lot, and it has a lot of different things you can do to it. One of the things you can do with it is you can dictate how the print function is going to end the line. By default, what it dictates is that when you print something, it ends the line by going on to by putting in by basically hitting the enter key. by putting in a new line so that the next time you call print, it's going to go on to the next line. Make sense to everybody? So we've got total is equal. So now over here, what we've done is that I said, I want you to print this out, but I don't want the line to end yet. I want the end of the line to, instead of being a new line, which is the default, this is the default, please print out a new line at the end. And this basically said, just keep it there until I do my next print statement, which I did, which was another tab, which because of the way tab works was smaller, it was that size rather than big size, and said after adding the total is this. So we see that it's 0, 0 becomes 0, 0 plus 1 is 1, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10.
Where does the program get end from? Like, what is end?
That is what we call a, that's built into the way function calls work. It's a default variable. So in other words, it's getting it from print.
So it just knows that total,
because
it just knows that total is adding those up, and that the end is going to be what the what is added up.
Yep. If I go into idle and watch this, see how, do you see that yellow thing at the bottom that popped up?
Yeah.
So values, and then the ... means as many values as I want. And then there's other then I can and then it says what variables it will recognize as default arguments. And so it's saying, these are separator, end, file, flush. Those are all things that by default I'll set to space, new lines, system standard dot out, and flush respectively, if you don't specify something. And you almost never have to. But if you want to change that for some reason, feel free to go ahead. Make sense?
Yep. Thank you so much.
And it's just useful for doing tricks like that. Okay. But now let's go on to our Leibniz formula. So we need to, this is going from this is going to go from basically doing some easier stuff to our stuff. Alex, did you have a question? Sorry, I saw your face for a second and I thought that was a face of.
Oh, no, yeah. I mean, the only question I have is, can I demo after class? But that's not relevant now.
And yes, you can. So, all right. Sorry. So we have this formula: 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 ... is equal to pi over 4. So what do we want to work? So this is like two difficulties over here. The first is adding in. So the first thing is that we need to be able to swap from doing subtraction to addition, subtraction to addition, subtraction to addition, right? So, and then the other thing is doing these fractions. So which part do we want to work on first? It doesn't matter to me which one we do first.
The addition subtraction.
Addition subtraction. Great. Okay. So let me go over here now that we're actually computing pi. Okay, so we're going to do this Leibniz formula over here. So the way that this is going to work is that we need to do addition subtraction. So let's do our total is equal to our total is equal to 0. We're gonna do the accumulator pattern like we did earlier. And now what we're going to do is equal to, and iterations is equal to let's do with 5. So iterations is the fancy word of saying how many times did this run. So in other words, how many numbers are we going to add up? We could also call that terms for how many terms we want to add, but like it just depends on how you're looking at it. Is it how many terms we're adding together, or how many times this loop is going to run? And that's just simply, you're comparing two things that are the same thing. So for the way I can just show both screens is that I share my entire screen, then rather than one. So you have the option of sharing your entire screen, not just a window. So for value is equal to, and so now let's do with in range iterations. So let's start out simple. I'm not quite sure what you mean. I can try to talk with you after class about that. So what we have is, so rather than doing this 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, let's work on doing 1 plus 1 minus 2 plus 3 minus 4 plus 5. Does that make sense to everybody? An incrementing series like this, right? That's alternating. Does that make sense? And then we can eventually use that to go from 1 minus 3 plus 5 and so on and so forth. Make sense to everybody? So how can I do that? Well, I can do that by, well, first off, I know how to do this by just adding everything. Total is equal to total plus value. However, one thing I will have to change if I want to do one, if I want to start at 1, I do need to say 1 and then iterations plus 1. Rather than starting at 0, I'm going to start at 1. And then I add the plus 1 at the end because I added a 1 at the beginning. So it shifts it to the right slightly. It shifts it off by 1. So this should be 1 plus 2 plus 3. And yes, that is what we'll do. We'll be multiplying by a negative number. Print. Print total. So right now, so we're up to 15, which would be 1 plus 2 plus 3 plus 4 plus 5, right? So now we want to do 1 minus 2 plus 3 minus 4 plus 5. So how do I get the sign to swap each time? And it's a bit of a jump in logic, but it's actually not too hard once you understand the trick. I'm going to create a variable called sign over here. An if statement would do it, but I'm using the tools that we currently have, which is just the for loop and variables. So I'm going to set the sign equal to 1. And that's just because everything in this is either going to be either a value that's been multiplied by 1 or multiplied by -1, right? This value is 1 is multiplied by 1. This value is multiplied by -1. This value is multiplied by 1. This one's multiplied by -1. And it's very easy to swap from 1 to -1. You just multiply by -1. And it's very easy to swap from -1 to 1. You just multiply by -1. So what am I going to do here? I'm going to say, hey, multiply this value by the current sign. Okay. And then here's the cool trick, which is a bit tricky, which might be a bit tricky if you don't have a feel for this yet. Sign is equal to -1 times the sign. And now when I run this, I get 3. But let's print out let's print out what the value is. Print. Specifically, we'll print out value sign sign times value. And again, what I'm going to do over here is I'm going to do a middle modification, which I find very cool, right? Just like I can modify end, I can modify what the separator is when I put in things by values. Why don't I have the sign be -1? Because I want to start at a positive number. And now if we print this out, we'll see that here's how it works. For 1, we end up we have a positive number. 2 is a negative number. 3 a positive, 4 a negative, 3 and 5 a positive. So see how it's alternating now? What are you confused about, Kushi? Which part?
I really didn't understood like the print statement where it says value sign and then multiply by sign.
So what I'm doing is that I'm printing out the current value of value, the current value of sign, and then what we get when we multiply those two numbers together, right? So, right, the value is just 1, 2, 3, 4, or 5, right? Make sense?
Yes.
And
So
now,
we are only using 1, 2, 3, 4, and 5.
right. And now this sign, because that's what's dictated by iterations, is 5. And the sep, and I'll get into the sep in a second. That's something I just introduced. Print value sign. So that's going to be positive, negative, positive, negative, positive. So 1, -1. So 1, -1, 1, -1, 1. So they keep switching. And then I multiply them together and show you whether it's going to be, 1, -2, 3, -4. Now, what is sep is equal to tab? What that does is that if I don't have this, by default, the way things are separated, when I have multiple things that I give to a print value, when I have multiple arguments that I give to a print value, it gives me everything separated by spaces, which is just a bit hard to look at, right? It's not very organized. So what I can do is I can say, hey, if I give you multiple arguments, if I give you multiple things to print out, and each of which are separated by comma. So here I gave you 3 things that were separated by commas. Instead of printing them out as separated by spaces, I would very much like it, please, if you can print them out by tabs. And this was just a quick way for me to print everything out separated by tabs. Make sense?
So like this is like a multiplication table which we have in lab 4.
Kind of like it. It's kind of like that. Although with that one, you'll need a bit more. You'll need to nest those, which you'll learn about. So now that now we've got our alternating parts. Okay. So now what do we need to do? Well, it's not 1 - 2 + 3 - 4 + 5, right? It's 1 - 3 + 5 - 7 + 9. So first off, this number goes up by 2 each time around. Okay. So so how can I do that? Well, I could do that just by like going up by 2 over here. But then I'm only going to get 3 numbers out, not 5. So I could modify the mathematics though. So let's see, could I do value plus yeah, let's start at iteration. So let's go and do this. Let's start at iterations over here rather than iterations +1, because you can kind of see the answer, and this will make it a bit cleaner if I do it like this. So rather than doing this, I can say, hey, value you're going to change this to I. value is equal to 1 plus 2 times I. So that's quite a bit of swapping that I did there, but it makes it a bit easier for me. That is a way to do it, Andrew. So what I'm doing over here is I removed this so that it started at 0, okay? And then what I did is I said the value is equal to 1 plus 2 times I. So 1 plus 2 times I, which is 0. 1 plus 2 times I, which is 2. 1 plus 2 times I, which is, and I in this case would be 2, which would be multiplied is 4. Did I make a bit too much of a leap in logic there?
I have a question.
Yes.
So like for iterations, it is till like 5. So why do we have 9 and all?
It's 9 now because of this. Value is equal to 1 plus 2 times I. And value over here. Does that make sense?
Yes. So like I will go until 1 to.
I will be
So-
0 here. Let's go ahead and adjust this. Okay. So here we have I, the value. So here we have I, and then we have the value, which is 1. We have 1 plus 2 times I, what the sign is, and then what the and then what the total is. Which I could just, and here's another nifty thing you can do, why this is useful. It's good for making tables. I 2 1 plus 2 times 1 plus 2I there we go. So do you see what I have now? What I've done is that I'm starting with, I decided, okay, let me start at 0. What that allows me to do is that I can start adding 2 times I to 0. Sorry, and the reason, sorry, that allows me to start at, if I start at 0, then I can just say the value is equal to 1 plus twice I. So for the first step, that's going to be 1 because multiplying anything by 0 is going to give me 0. So this entire thing becomes 1. But then every time I goes up, this amount goes up by 2. Right? So every time I increases, this value goes up by 2. Then this value goes up by 2. Then this value goes up by 2. Does that make sense?
Oh, yes. So like every time we assign the value for sign, it is 1 only.
Yeah, all we're doing when we're with sign, all we're doing is that we are, so sign starts out at 1 because it's outside this for loop, okay? And then every time I'm done with doing all my computations, what I'm doing is I'm doing -1 times sign. And what that's doing is that it's multiplying sign by -1 and storing the result in sign. Essentially,
Oh, so like, so like first we'll have positive number and then the negative.
Yep, it's swapped, and that effectively allows it to swap between the negative and the positive. Okay.
Yes, thank you.
Now for the last part, which is okay, which is actually the easiest part, which is okay, but how in the world do I turn it into a fraction? Just put it in, you know, just put it in a fraction. Now for the first value, this isn't going to be too bad because it's still going to be 1. What's 1 divided by 1? So now over here, we're getting some issues where basically that the values are a bit too big for the table because of repeated stuff. And that's going to go into making it gets a bit tricky at that point to make it pretty. But point being is that, right, we've got 1, 1/3, 0.2, that's a 5th. And then this is a 7th, and this is a 9th. Okay. So now let's go ahead and do so I'm going to comment this out because now, believe it or not, we've got our approximation done. So our target, so I'm going to type target is equal to, so this is our target because the equation gives us pi over 4, right? Makes sense? Our target is pi over 4.
Yes.
So, and this is what we get. So here, and again, I'm going to comment this out. Our target is this, and we end up with this. If you prefer, would you prefer me the target to be pi or pi over 4? Because all that, because I say pi because everybody knows what pi is. So since our target is now pi and the equation gives us pi over 4, all I'm going to do is multiply by this by 4. So we turn it from pi over 4 into pi. So our target is 3.14159.265. Okay. And here our approximation with 5 digits gives us 3.3396, which is not pi. And so, yes, Conrad, you've got it right. If we increase the number of iterations, right, the closer this gets to infinity, the more accurate it's going to be. So notice here, we've got 3.13 after doing 100 iterations. If we do 1,000 iterations, another factor of 10, we start seeing some results. Our target is 3. And let's go ahead and make this a bit more easier to read by lining it up. So target value, and then we needed, and this is again where tabs become really handy for just lining your stuff up. Okay. So 10,000. And note that it's, getting closer. Also notice here's something. I'm doing 10,000 of these addition, multiplication, and division operations. And the computer's just doing them instantaneously, 10,000 of them. If I go up to 100,000, there's just a little bit of a lag right there. May have been too slow for you to notice. Okay, now let's do 1,000,000 iterations. Yeah, and you should have been able to see it there. The computer just started, there was a slight delay between the target and the value printing out. Okay, because if I'm doing 10 times the amount of iterations, so now we're up to 10 million, then it's going to take 10 times as long for my computer to do. So there we go. So here, doing this 10 million times got me to 3.14159.2 with the difference starting over here at 5. And if I were to, and then if I run this now, it's going to take 10 times as long. And it's also not necessarily great to do it on a laptop, because your laptop's great at what we call burst computation. It's for the heating profile, a lot of it is designed to give you bursts rather at high gigahertz. And then to make sure that you don't overheat, it will quickly throttle off. but still ran in a reasonable amount of time. And this is true because a lot of things that are intensive, a lot of common computing tasks that are intensive, don't really last that long. I mean, now, again, that's not like anything against laptops or anything. This is specifically the way laptops are designed to meet the majority of customers' demands, which is that laptops are, you want good battery life, which means you don't want the computer processor running full throttle all the time. And you want it to be cool, be able to be cooled and not painful to hold, which means that you don't want the processor going full throttle all the time. So using this, we were able to get to our target of pi.
So to find pi, all we needed, the two equations that we needed are the value equation and the sign equation. And then to find pi over 4, we needed the equation that you have that's got the pound sign next to it.
I mean, these things were just my notes as I was building up.
No, the one below the value equation.
Oh, here?
Yes.
This was just simply printing the, this was just simply show my notes to show as I was printing out to show you what was going to happening. The formula is this Gottfried is the Leibniz formula over here. 1 minus 1/3 plus a fifth. And so what we did is that it's this over here.
Oh, I didn't see the times 4 down there. I'm now seeing the times 4 at the bottom.
Yeah.
That's what you changed.
So I went from time.
Okay.
So I multiplied that by 4 so that I could target pi. If I wanted to not modify that, then I would have to do it like this, right? Where our target is now pi over 4. Make sense?
Yeah, I just missed that 4. I thought that when you turned that function below value into a note, I thought that changed the equation.
I've been making a lot of minor adjustments here. Now, why did we do this today? Mainly because I find this an interesting way to build up what looks like a complicated math equation. But it's also to kind of to tell you about a point for those of you who whose philosophy is similar to mine, which is, why am I learning all this mathematics? I can make the computer do it for me. There are courses called specifically Numerical Analysis, which is basically designed to do that. The idea is this math is too hard. I'm going to make, so I want to create an approximation of the answer that is close enough to being correct. And that's very useful because computers can do those approximations very, very, very quickly. The idea here is that, again, the computer can only store so many digits for a number. Eventually, the error that from your approximation is going to be less than the error that your computer can store. So it's going to be the same answer anyway. And this is one of those formulas. Eventually, I could get to a point where it doesn't really matter. There are a lot of, there's different approximations of pi, list of formula involving pi. Let's see. Other infinite series. Looking for see, Leibniz formula for pi over here, Madhava series over here. Then there's this series over here, which relies off of this. Is there a product series? I believe there's supposed to be a product series. 1 second. Name of that would be, oh yes, the Wallace Formula. Similarly, if you want to get more practice with this, because class is almost over, you can try this formula, which is a formula from 1656. And the fact that they figured this out is just shows how much free time they must have had on their hands. Because over here, right, instead of doing an infinite a summation, this is a infinite product. So 1/2 so pi over 2 is equal to 2/1 times 2/3 times 4/3 times 4/5 times 6. So every so often we're increasing these by 2, and then we're increasing, so basically we're alternating which one we're increasing.
Quick question.
Yes.
The wrong screen.
Sorry.
Are you sharing something right now?
Yeah. Is the chat not update? Let me guess. Yep. Zoom is acting up again. Okay. Yep. 1 second. Yeah, don't feel free to interrupt if Zoom starts acting up. I'm sure this will be fixed in the next update or something, but yeah, this is a issue with Zoom. So the Wallace formula, if you want to try that, it looks very scary, but this is something to try if you want more practice at doing infinite summations. Pi over 2 is equal to 2/1 times 2/3 times 4/3 times 4/5 times 6. So these top two numbers increment by 2 and the bottom numbers increment by 2. So, and you can use this formula over here to see how it's derived, which is you start at 1 and you go all the way up to your target value, and each term is this value. So that's another one we could do. I do it, but I spent a lot of time going over, making sure that I was doubling back and getting to important bits. What is so before I end up class, because you might be feeling totally lost and stupid at this point. First off, you ain't stupid. Okay, so get that. So stop thinking that. You're just suffering from imposter syndrome. Okay, it's important to recognize the difference. This is a bit of a reach, and the only reason I'm able to do it is because I've had practice doing it. And I'm trying to see how much I can challenge you with doing this kind of mathematics. Okay, what was important for you to get today? The important thing was actually understanding what goes on in this first file, the use the force file, which is basically understanding that not only can we, how does the range work, and the fact that we can get the values out of a range of numbers using for I or for value in range, and then use them in interesting ways if we need to. Okay. The pi calculation was a reach, was our reach. Basically me pushing you to do as awesome as you can. So it is 3:20. That is the end of class. The only thing I'll say is that I will post details of the next quiz on our on Canvas. And that and if you have issues with the quiz, please check the announcements / your email / the Discord, where basically I put out a form that if you need partial credit for a question, or you think that you're deserving of more partial credit, just submit it. Just basically fill out that form. It will automatically, I'll be automatically see everybody who filled it out, and it's just a centralized place, so I don't have to sift through, the 50 bajillion emails I get every day. and to figure out who I need to regrade. The quiz should automatically tell you what you got. Just click on the quiz and look at the top of your screen for your auto graded score. The new quiz, if I recall correctly, it's about turtle manipulation, but I will let you know. All right, so I'm going to stop sharing my screen.
Professor, I have a question.
Yes.
It has to do with the pi problem. I was really confused at how you had like the pi problem and you had range, and then you only had like one answer instead of all of those other answers. Why was there only just one?
Or when you mean this, when I was this thing where I had one?
Yeah.
I commented out the table when it was starting to get ugly like this.
Okay.
I started commenting out the table because the repeated variables was making it very ugly to look at. Does that make sense?
Yeah, I can see that. Okay, thank you.
No worries.
Professor, where did you say the form for the partial credit would be?
Check the announcements page on Canvas. Check your email. If you're receiving announcements I send out from Canvas, then the announcements are also cloned to your email. And finally, check the quiz issues channel, the quiz issues room in the Discord channel.
Okay, thank you so much. Have a great day.
Yeah, if you
For the
can't find it,
chapters on Runestone, oh, sorry, I didn't mean to interrupt you, but for the chapters on Runestone, I overlooked one of the due dates, and so I didn't do it until today. Like when you run it, is it still possible to get full credit for that?
yes.
Okay,
The due dates on Runestone, the due dates on Runestone, except for the quizzes, are as soft as my cat's fur.
Okay, perfect. Thank you so much.
I have
Have
a
a
question
good day.
about the quiz.
Sure.
So for the quiz, it's saying that I skipped all 4 questions and I have a 0%, but like the first time I took it, when I took it, it said I had a 75%.
That's
and then I left and came back and it says now that I have a 0%.
Did you hit the submit button?
Yeah.
Okay. Can you send me an email, because I will need to look into that when I get home in more detail on my
Okay,
side.
thank you.
I'll need to look on my side because I can see your interactions with the quiz. Okay.
Okay, thank you.
And yes, you can demo with your TA. Okay. All right. Let me see.